Well, welcome everyone to our electrical engineering seminar today. I'm very delighted to welcome my colleague and friend and lab mate even, Dr. Miguel Morales from physics. Miguel got his bachelor's degree in physics from Swarthmore and taught high school physics and astronomy for 3 years. That's interesting. Then went to UCSD where he got his doctorate in physics. Miguel's graduate work involved searching for very high energy gamma ray bursts. In 2002, however, he got a postdoc and moved over to the better side of astronomy, the radio side of astronomy, and became a lead designer for the Murchison Wide Field Array in Australia. Miguel now is investigating the earliest stars in the universe, as well being quite well known for innovations in high-speed correlator design. If there's one thing radio astronomers can do better than anybody, it's correlate a lot of data. Miguel has won many awards and scholarships throughout his education and research, and the UW has been fortunate to have him here since 2008. So Miguel, I'll invite you to come up and tell us about imaging the noise, galaxies and the hiss.
Well, thank you. It's fun to be here, and one of the things I want to encourage you to do is ask questions as we go along. In particular, because some of the language, I tend to talk to physics and astronomy audiences, and you don't even remember when you get into jargon sometimes. And so please feel free to stop me and go, what the world was that? Of course, I'm really the figurehead of a group, so this is my group here at the University of Washington, and basically what I'm going to be presenting is the work that they've done, and I occasionally try and supervise them. So, actually, because this is, my home lab is only across campus, I got to bring one of these in. So this is just a radio antenna, a simple dipole, 2 cross dipoles with 2 little low noise amplifiers in the middle there. And it works between 80 and 300 megahertz, so sort of in wavelengths. That's, sort of order a 2-meter wave, which is why this is the size it is. It's kind of half a wavelength across or whatever. So this is really dirt simple. And so what I'm going to be talking about today is mostly the Murchison Wide Field Array. And so the question, there are 2 questions, I guess, but the main question is how do we take 2,000 of these and make a telescope? Is the first half of the talk. And then the second half of the talk is what in the world do you see? And I think one of the things that's kind of interesting is particularly as parts have gotten better, particularly driven by the developments of cell phone, analog, and digital electronics, if you take this here and hook it up to a spectrum analyzer, you see a lot of radio signals and stuff like that. And of course, you can also measure, there's always a little noise on any measurement. And the interesting thing is that it turns out that these amplifiers have gotten so quiet that the majority of the noise is not electronic noise. That is completely subdominant. In fact, the majority of the noise is coming from the sky. And so I want to talk to you about what that noise is and what kind of drives it and things like that. And so the way to do that is to take a bunch of these and measure the noise very clearly by building a radio telescope. And then we can go down and see what's there. And we'll go down through various levels of noise as we go deeper and deeper into the kind of signals we're looking for. So, okay. But let's give a science motivation. So why would one spend as much time as we have trying to build something like this? So I'm a cosmologist, so I'm allowed to put the entire history of the universe on one slide, starting with now, starting with the Big Bang and going to now, 13.7 billion years. And the universe is quite simple. But one of the interesting things is if you look back far enough, you'll see a wall of glowing gas if you look in the microwave at much higher frequencies. And that's called the cosmic microwave background. And there's all sorts of things that you can learn by looking at the cosmic microwave background. But for the first part of the story, it's incredibly smooth. It just looks like a wall with little fluctuations at about a part in 100,000. But if I look later with something like the Hubble telescope, you see stars and galaxies and clusters of galaxies. And so the question we're going to start going for is how did we go from a very smooth universe to a lumpy, clumpy universe much later? Well, to do this, we're going to go look at hydrogen. So the majority of what is in the universe is hydrogen. The universe is made up of hydrogen, helium, lithium, contaminants like you and me. And so let's just look at the phases of hydrogen. And so hydrogen comes in two flavors. It comes as a neutral atom, where an electron is hooked to a proton. And it comes as a plasma, where the electron isn't hooked to the plasma. And you start off very early on, and the universe is a hot plasma. The conditions are actually very similar to the outer parts of our sun. So you have electrons and protons running around with tons of light bouncing around. And so every time an electron tries to hook onto a proton and go jumping down through the energy levels, it immediately gets hit by a photon and knocked back off. But the universe then expands and cools. And the rate at which those photons are molesting atoms falls. And you get to an important time where all of a sudden there's enough time for the electron to hook onto the proton, fall down through the energy levels. And when that happens, the universe goes through a phase change. It's like freezing of water. You go from everything being a plasma to everything being neutral. And suddenly you've moved from a plasma to neutral gas. And in fact, that is what we see when we look back at the cosmic microwave background. It's that last wall of plasma. Then not much happens for a while. Gravity starts slowly bringing the gas in. Eventually, the first stars and galaxies start lighting up about 700 million years later, after the Big Bang. And stars and galaxies, stars can then emit ultraviolet radiation, and those ultraviolet photons can then kick electrons back off. But something important has happened in that 700 million years. The universe has expanded so much that when you kick an electron off a proton, it now takes it a very long time to find a proton to hook back onto. And so it doesn't then take a whole lot of light from those first galaxies and stars to then drive you back through another phase change, this one lumpier and bumpier, to then make the universe entirely ionized. And today, the universe between the galaxies is ionized to a part in 10 to the 5. It is absolutely ionized. And so we have sort of pictures of what that might look like. So here's a movie, not a picture, a movie. So this is a theorist movie. And so the green are early galaxies, which are starting to light up. The stars from there are sending out photons, which are burning holes into the hydrogen by ionizing the hydrogen. And so you start getting all these holes. They start then overlapping and following the tracery of large-scale structure, the filaments of galaxies that exist. And then eventually these keep overlapping and growing these bubbles. You go through an interesting topology change here, where you go from bubbles to islands of neutral gas. And then towards the end, it fairly quickly finishes reionizing. And I have to wait a moment to let it finish reionizing. It finishes reionizing, and then you are just left with the green galaxies filling the inner cluster space. So that's what we want to do. That's what we want to see. So the instrument we've built is called the Murchison Wide Field Array. So step one of this is, why does it have such a funny name? So it's a collaboration. It's a US, Australian, Indian, New Zealand collaboration with a bunch of different universities. And the name Murchison comes from the Shire of Murchison, where it's located, which is about there in Western Australia. You'll notice there aren't any roads there. Now, the reason astronomers are known for going to the ends of the Earth for the best locations, whether it's the mountains of Hawaii or the Atacama Desert in Chile. And this turns out to be one of the great places in the world for radio astronomy. And the reason is it's incredibly quiet. So here are 1 hour spectra with a astronomical radio telescope. This is megahertz in various different bands. So you'll notice, hot 102.1 FM, be right there. This is right through the FM and TV broadcast bands. And we have the feeling that it's hard to describe how bright radio transmitters are. We kind of tend to feel that you guys are kind of profligate in your use of power. Whenever you have a problem, just crank up the power, and that starts getting to be problematic when the units we work with, a nice bright radio source for us is 1 Jansky. That's 10 to the minus 26 watts per meter squared per hertz. So that's not a lot of juice coming in. When you guys start throwing megawatts off of Queen Anne, it starts hurting. This, for a radio astronomer, is stunningly quiet. No filtering going in that. Another way of showing this is if you look up with our radio telescope, you see that little moving spot? If you look in the FM band, that is the International Space Station in reflected FM. This is effectively passive radar. And actually, if you look at the FM stations on that, you can actually figure out which ones are uprange and which ones are down by the Doppler shifts of the spectra against that. It's also a pain in the ass to get to. So if you get on an airplane here at SeaTac and your connections go well, you get off in Perth 27 hours later. Then you drive 6 hours to the town of Pindar, which has 4 houses, no gas station. And you get on that road for 4 hours. Then you get on that road for another hour. We are in the Shire of Murchison, as I mentioned, which they're very British shires. It's kind of their equivalent of a county. It's about the size of Massachusetts plus Rhode Island, which aren't the biggest states, but it's a fairly big, large area. And the population is 120 people. The reason we're there is there have been so few people. No one's ever broadcast FM and radio TV out there. There wasn't enough people listening to pay the power bill. So let's talk about the telescope. So we finished building in July the telescope. That was my postdoc, Brenna Hazelton. Here's my grad student, Adam Beardsley, actually going out and arranging all of the antennas. Where you place the antennas determines the point spread function or array beam of the telescope. And so he did a lot of work on that. Then you do some trenching in the desert because you still have to meet code. You put some fiber and some power in the desert. Then you get a mesh ground screens that the little dipoles are going to sit on. And you lay out the ground screens and you take these antennas, which come in kit form from China, custom designed, but built in China. And you slide them together and then you snap them onto the grid. And so you put down 2,000 of the dipoles, and they're arranged into these tiles. So we have 128 of these tiles. And you'll notice that, so you have the cables, and they go to that box. And so one of these tiles acts as one antenna. And in that box, which unfortunately I don't have a picture of, is a circuit board, which has nothing more complicated than a series of different wire lengths on a PC board. And so you can digitally choose the delay of the signals. So you can take all of the dipoles on one side relative to the dipoles on the other and delay the signals and move where the antenna is pointing without any moving parts. This is just aperture synthesis. But you can just, by changing the delays, you can step your beam around the sky. Typically, this is about 2 wavelengths across, so we have a beam from each antenna, which is about 30 degrees across at usual frequencies. These are the Australian undergrads who assembled all the antennas. You then get to hook them to digital systems. So this is our digital crate, which is in the field, is essentially an analog to digital converter, a polyphase filter, which is then chunked to pull out 31 megahertz of bandwidth, and we can pull out which pieces of that we want. It's then conditioned and put onto a digital fiber, and each one of these serves 8 antennas, each one dual polarization. So here's actually hooking up all the antenna signals. It also is the command and control for that. Each one of these boxes is sealed and environmentally doubly sealed with Faraday cages because you may not think about this, but computers radiate radio noise, so everything is sealed very carefully. So we seal this, and then you have little air conditioners to keep them going. There's then some fiber, so we ship the fiber out. Here's our patch panel. It's then moved about 10 kilometers to where the main computing happens. So this is a GPU accelerated cluster to do the main correlation, where we channelize again in frequency, and then we do all-pair cross-correlation in GPUs. So you may be familiar with phased radar, where you time the signals from all your antennas, and they will add up in one direction. We're just time reversing that. So you could make phased array beams around the sky, but computationally that's expensive to do a different beam in every location on the sky. And so instead what we do is we do the correlation product, which is a cross multiply between every pair of antennas, and that does go as n squared. And so for 120 antennas, each with dual polarizations in 3,000 frequency channels, we do all pairs for each frequency. It gives us about 2 billion visibilities, if memory serves, every half a second, where visibility is a pairwise power between these antennas. And then we can take those to make images. This gives us about a terabyte of data. It reduces our data rate from about 16 billion samples a second across the array down to a mere terabyte an hour data rate that we actually have to store. And then here's some pictures. So this is the core, and you can see all of the various tiles along with a couple of the receiver boxes. And if you back up, you can see a few more of those hard to see. These things are kind of spidery, so they're kind of hard to see in the desert when you fly around. But anyway, we have 128 of those. That's the radio frequency range, full cross-correlation, and close attention to systematics. And when you look up, and we've collected a petabyte of data just for my science project since July. We'll talk more about that later. Once you have that petabyte of data, you have to analyze it, i.e. make images of it in many frequencies. I'm actually, because we've had to write all our own custom software for this to push the state of the art, we actually have 2 pipelines, a US pipe and an Australian pipe, and I'm the one who's organizing that effort for the analysis of that couple of petabytes of data that were coming in. If you want to talk to me about this, I can make you all, I can talk at length. But if you then look up and just make a picture, this is what you see. So this is about 30 degrees across. This is actually looking at the galactic anti-center. So these are supernova remnants down on the left-hand side. Those are stars that exploded a long time ago. You actually have the plane of the galaxy, which is weak in this direction, going up diagonally. And then you have all these spots. Those aren't stars, interestingly enough. Those are all galaxies. They're radio galaxies. To go look at one at slightly different frequencies, what a radio galaxy is the white bit is what you see optically. And this is an elliptical galaxy. And then you see these huge radio lobes around them. So every one of those spots on the previous picture was something like this. And what that is it's a supermassive black hole in the center is accreting matter and ejecting it along the poles at very near the speed of light. And those go out and then crash into the very thin gas in the intergalactic medium to form these large lobes. The electrons in there are spiraling around through magnetic fields, emitting synchrotron radiation. And then that's what we see. So what you're seeing is galaxies. And this is, or if I go back one, that is the primary noise that you see. The hiss that you see in the antennas is some from our galaxy, some from all the other galaxies. They're about equal parts. And that is the primary source of noise. And if you actually correlate it and look up, the sky is full of galaxies. Now, in certain ways, the talk is done. But I wanted to keep going and talk a little bit more about noise and go further down. Because it turns out I'm not interested in this. This is just in the way, right? These are nearby galaxies. I want to go look at the first, I want to look 13 billion years ago. There's a question.
From somebody who doesn't know about radio, what would this be like during the daytime if we had our own sun?
Yes. Oh, there's a picture I wish. So our sun is quite bright in radio, but you can still see, you can actually do astronomy as well because the atmosphere doesn't scatter light. What makes it hard to do optical is the fact that our atmosphere is scattering the sun's light to make it blue. And so it actually still appears dark, and you can see all the galaxies during the day. The main problem with the sun is that it's not steady source. It flashes with coronal mass ejections and various other things going on. So it's kind of strobing away in the side. So we actually do all our are sensitive science observations at night for that reason. The reason, there's a picture I forgot to put in my talk this morning. We had a partial solar eclipse about 2 weeks ago. And it's actually kind of fun because you can see the sun, and the sun's actually bigger in radio than it is at optical. And you can see the corona, and then you can see the moon's shadow taking a bite out of it, just by staring at it. So, did I answer the question? That's a good question. All right. So, I wanted to study this, right? This is the picture I want to make. But despite having 2,000 antennas, even if I look at one spot for 600 hours, it turns out I still don't have the sensitivity to make an image. The picture here will be below a signal to noise of 1. So I still have to then go do a statistical measurement of that. So let me just stop for a moment and describe a little bit more of what I'm looking for. So unlike synchrotron emission, all those galaxies that we were looking at, which were electrons spiraling in a magnetic field and thus emitted at all frequencies, hydrogen, what signal are we looking at? Well, if you remember back, and some of you may not have had this, to physics of the hydrogen atom, you have the proton and the electron have spin. And so the ground state of hydrogen, where the electron's in its lowest energy level, there are actually 2 quantum states. There is the parallel and anti-parallel states, and those have a slight energy splitting. And so you can get a photon emitted there. Now that photon is very, very low energy, and because it's low energy, it has a length of 21 centimeters. That's why you can't put radio, any kind of broadcast in 21 centimeters. It's owned by radio astronomy so that we can look at our own galaxy and look at other nearby galaxies. That whole band is owned by radio astronomy. But we're looking a long way away, and so it's been redshifted. And so while it started out at 21 centimeters, it's been redshifted by a factor of 10. So now we're talking about a 2-meter wave. And that's why we're off looking in the FM and radio broadcast bands. But it's also a line emitter. It emits an incredibly narrow line, which means that instead of seeing a surface, I actually get to see a volume, because you have the surface here, but the part at the front has less redshift than the part at the back. So if I look in frequency, this part shows up at higher frequency, and then a little lower, a little lower, a little lower. I can do tomography all the way through. So I actually am viewing a volume of space because it's an optically thin emission line. That is a key step that we're going to play. So, but again, I want to make a volume, but I can't quite do that. So let's go play some statistics. And I'm going to take a detour here. This is not my measurement, but this is another way of doing what's called a power spectrum. So this is the cosmic microwave background, and it's beautiful. You should all have a picture of this on your wall. But there's an interesting question of how do you get science out of it? How do you turn that into a picture into science? And well, one of the questions you can ask is, well, I don't care about the light, where it's bright and cold, but I want to know what size brush was used. It looks like a pointillism painting. Was this completely random, or were there certain preferred brush sizes that were used? Now, the way you will do that is an analog to a spectrum, a power spectrum as you guys know it, where you would take an electrical signal, do a Fourier transform, square to get rid of the the phase and do a power measurement, and then average in time. And if you have a weak signal, your noise will slowly average down, and you can see spectral lines. We're going to do the same thing, but we're going to start with an image, so it's already in power. But we're going to take a Fourier transform of this, but not a one-dimensional Fourier transform. We're going to take a two-dimensional Fourier transform. Now, this is actually on the sky, so we do spherical harmonics, but it's really a two-dimensional Fourier transform. And then we're going to say that there's no preferred direction in space, so our average is going to be over rings, or for spherical harmonics, M's, to pick out various things of different length scales, different spatial frequencies. Just if you think about something like this as being a long scale and something like this as being a short scale, and they end up at different frequencies, we're going to do different spatial frequencies, i.e. different brush sizes. So if you take this picture and you do that, this is what you get. If it had been pure noise, it would have been flat. If there had been one brush size used, it would have been nearly zero everywhere with a great big spike. Instead, what you see is these beautiful ringing patterns. Ooh, man, that's kind of fun. These are called acoustic oscillations. So what happened in the early universe is we have a plasma. This is before everything went neutral. But it's kind of bouncy in that when I squeeze it together, the photons then push it back out. But if I pull it apart, the gravity pulls it back together. So if I start it, it rings. And if I start something about this of a certain size, and let's say it's a little overdense, so it starts gravitationally coming in, and then it overpressures, and it's about to turn around when the picture of the CMB was taken. So you get a bunch of things of that size. Something half that size had time to compact, rarefy, was about to come back when the picture was taken. And something a third that size, compact, rarefy, recompact. That's the first peak, second peak, third peak out there. Now, if it had been a really nice, bouncy thing like this, you would expect all the peaks to be about the same size, as they would just keep ringing. But you get this really fascinating pattern where the first peak is great, the next one's small, but then the third one's pretty good again. What that means is that gas the first bounce wasn't very good. It just kind of went squish. Just, and then the next bounce was pretty good. That's dark matter. Dark matter doesn't see the photons. So on that first bounce, it gravitationally helps pull everything in. All the baryons, all the matter that we normally know about, bounces, but the dark matter doesn't. It keeps going and makes that first bounce squishy. But after it's decoupled, the next bounce is pretty good. And then there's some damping, which occurs at higher frequencies. Our best evidence that dark matter exists is the ratio of those first three peaks. We know not only does dark matter exist from the way our galaxies move, we know dark matter had to exist 13 billion years ago. Ooh, that was fun. Let's go do it again. But let's go to 3D, right? 2D wasn't enough. So let's do 3D. So now I have an image cube. All right, and I've got that over here, angle, angle, frequency. And I'm going to do a three-dimensional Fourier transform over to that direction. Now I'm going to use the same trick in that statistically, there's no preferred orientation in space. It's rotationally symmetric at a statistical level. So in my image, a rotational symmetry is, in the Fourier space, a spherical symmetry. And so when I do that, if I look at the right-hand Fourier representation, all of the measurements within one annulus are from the same statistical distribution. And so I can square average within that annulus to get one measurement of the size, the number of bubbles on that particular length scale. And so again, I'm doing a spatial frequency, Fourier frequency attempt at this. And so then I break this into annuli, and then you will end up, again, with a power spectrum of different size bubbles that goes out. It turns out for the rest of this story, I actually want to go somewhere else. And so 3D, this is really a 3D power spectrum, right? If I go back one. 3D images are really hard to show. So I'm going to take it and I'm going to say that there is a symmetry on the sky. So I'm going to sum across the sky directions. And I'll call that K perpendicular, where K is just the Fourier wavelength that I've taken on the sky. And then K parallel, which is the line of sight direction. And then my shells have become rings in this space. And I'm going to come back. This is called the K-perp, K-parallel space. It's become kind of the figure of merit for this field. So you already know why this is hard. The problem is that I've got all these damn galaxies in the way. I see the light from our galaxy. I see the light from all these other galaxies. At 600 hours, we will average 100 galaxies per pixel. The sky is absolutely full. Now, this is the point where most people go screaming off into the night and say, you can't do this. But we're going to use that symmetry to our advantage. You also get all sorts of other things, radio recombination lines, RFI, that's you guys broadcasting, television and things like that. And we'll come back and talk about that. But let's go back to our image cube and look at what a galaxy looks like. So I have a galaxy. It's a spot. But because it's synchrotron emission, it's emitting at all frequencies. So it appears as a pencil beam through my image cube. Now, those pencil beams can cluster on the sky. And in fact, spatially, it's a slightly red noise spectrum. But they don't cluster in the line of sight. They're very, very smooth. So in the Fourier transform of the line of sight distance, it all ends up in the first few frequency modes at the low frequency band. It ends up as a plane, or if I go to my 2D spectrum here, all of those foregrounds end up here. And they're stunningly bright. They're 4 orders of magnitude brighter than the signal I am looking for. But they appear down here versus where my signal was. And that was the state of the art about 3 years ago. But there's one more problem. If your instrument was perfect, this is what you would get. But we all here don't deal with perfect instruments. We deal with real instruments. And we get a few additional interesting effects. So if I look at a galaxy, a star, something small that's bright, I don't see just a perfect pinprick. It's not a mathematical delta function. I see that even though it came in as a delta function, I see that source plus what we would call the point spread function or the array beam. What would you guys call it here? I don't know. Point spread function. So what you see is so for optical telescopes, this is an airy disk. So what you would see is a bright star and then a series of rings around that star. And it depends on where you put your antennas as to exactly what your point spread function is. But I've drawn something here, which is essentially we have a missubtracted source, so it's a peak, and then a series of rings around that source, which spread out. The problem is your instrument is inherently chromatic. The size of my array, which sets the point spread function, while it's fixed physically, the number of wavelengths across changes as a function of frequency. It's just simply bigger at high frequency. And thus my point spread function is smaller. And so if I have here a source that I haven't quite removed right, and so I've got its rings coming out, and I'm interested in another location here. At one frequency, I may be at the peak of a ring. I move up into frequency a little bit. The rings move. I'm now at a trough of a ring. I go up in frequency again. I'm now at a peak. And now I have a ripple in the frequency direction. Oh, that's painful. I've taken these foregrounds, which were all smooth spectrum foregrounds, naturally, and I've thrown them in the frequency direction by coupling the chromatic nature of the instrument in with my measurement. It turns out there are a whole bunch of other things. They're polarized foregrounds. Synchrotron emission is highly polarized as a function, so it has a polarization angle, but it comes through the galaxy, and as it does, it is Faraday rotated, so the angle is rotated because space is birefringent due to magnetic fields, and that's a frequency-dependent effect. So as a function of frequency, the apparent polarization angle rotates. If my antenna is a little more sensitive to one polarization than the other, I see beating as it lines up or not with that. And you get multiple Faraday rotation depths at different things. We have antenna beam dependence. This list goes on and on and on. And the real worry is that it's taking all these foregrounds down here, where I'll never observe something, but throwing it up into the region where I might. And so starting with some precision simulations, and here again you see foregrounds put in which are exactly where you appear, but they're being thrown up. But they're being thrown up into a wedge. And this really mystified people, so we went off and looked at it. And I apologize, but I've got one more Fourier space. We've done 4 of them. I've got one more. So what does the instrument really measure? My instrument, all radio arrays really work in the Fourier domain, the spatial Fourier domain. We call that U for no better reason. So this is the spatial Fourier transform of the sky, but then you measure it at many frequencies. So this is an intermediate representation. I took my image cube and I Fourier transformed it on the plane, but I kept the frequency. That's naturally where our measurement is. Or another way of thinking about it is every pair of antennas is really making a measurement in that plane. So one more, this is our last Fourier space. But I'm just going to make a very simple model. I'm going to put in one source in my sky, a delta function off-center. The Fourier transform of a delta function is going to be a plane wave. And I'm going to make that source the same intensity as a function of frequency. So that's what these ripples are. It's a plane wave that's the same at all frequencies. So it's just a simple, one single source off-center. As I move it farther off, how close together those ripples get, they get tighter and tighter. And we'll leave the frequency alone. These lines then represent measurements by individual antenna pairs. And while they're a set physical distance, when I'm measuring this in wavelengths at higher frequencies, they're farther apart. And so they're actually taking a angled slice of measurement through this. And the pitch of that angle increases as I move to longer and longer baselines, larger and larger antenna separations. Okay. Let's zoom in and see what that does to us. Now, each measurement, so here again I have my corrugation on the sky. I've just zoomed in. And this is my antenna separation. But my antennas don't measure at one spot. Literally, I had 2 antennas, and they did a sum of the electric field over their aperture and put those into a cable, which you then digitized, and they did it again here. So they're really, if I look at the separation between those antennas, it's not the centers. There's some which is separated less because it's the near edges, and there's some which is separated more, which is the far edges. And so if you do this carefully, it's actually an integral of this plane. So the signal I get is an integral given by the footprint of the antennas. And that gives me a measurement. And then I do it again and do it again. And you'll see the amplitude of that measurement goes up and down as it cuts across those troughs, just as I would expect. So now I have a number which is increasing and oscillating up and down. But now I need to do something with that number. I need to make an image of the sky. So what I'm going to do is I'm going to regrid that number back down. But I can't put it right here because not all the number came from that location. It came from this integral. And so the best thing I can do is I can smear it back out. And so I smear it back out, and again you see sort of a large value, small value, large, small value. But the last thing I need to do is then take a Fourier transform in the line of sight direction. And if you look along the dashed line, you'll now see I have frequency ripple in the line of sight distance. And that frequency ripple depends on 2 things. It depends on how quickly the source ripple is going. The faster the source ripple, the faster that line of sight ripple, and the pitch angle of the measurement, i.e. the baseline length. You go do a little math, and what you end up with is some things. It gives you a simple relationship. All the stuff in parentheses is 0.3. It's cosmology. But what you end up with, sources near the field edge give you a band there. Sources near the center of the field give you a band here, and of contamination which has been thrown. And so this is the explanation of the wedge. The nice thing is when you get to the edge of the field of view, it cuts off. And that leaves you a region, which is now known as the epoch of reionization window, where the contamination should be very, very low. And thus, even though the foregrounds were 4 orders of magnitude brighter and some of that power through, there's a region which should be quiet enough to where we can actually go do this measurement in that region. Here it is in data. This is real data on the sky. You see that very distinct wedge shape, where it falls by orders of magnitude at the expected location. It turns out this is fundamental. People ask why might one do this, and you could deconvolve, or you could grid in meters instead of wavelengths and all this. It turns out you can't get rid of this problem, because the source of it was that sum that your antenna did, in that it literally did an integral over the electric field hitting the dish. And thus you lost information on where the signal was coming from across that aperture. And that fundamental loss of information is really what generates this wedge shape. Anyway. Turns out there's lots of fun. We can also understand how various different things fit in. We can then see what different kinds of mistakes make. Amplitude errors give you something flat. Position errors give you something which is sloped in its amplitude that we can go through. And there are a bunch of then different ways where this has become incredibly powerful to us, because we can actually identify statistical errors in the measurement which are below the noise limit. We can take two images which are identical to the error bars, and see the statistical difference between them and identify mistakes in the instrument that then led to those. And that's basically what my group now does. But you guys have been very patient, and I've stopped with Fourier spaces. So let me just show you a little bit of early data, which we've been having fun with. So this is the galaxy. So we're just taking a stripe along the galaxy. You see all these little lumps and bumps? That's the galactic center, various little circles there. Each one of those are a supernova. These are stars which have exploded in the past, lit up bubbles which have lots of electrons running around in them, and thus are glowing. That is the galaxy that we can see from the southern hemisphere, which is something like, oh Lord, 200 some odd degrees across and 15 degrees wide. It's about 15 minutes of data for us. The epoch of reionization, so you can see the galaxy here. This is actually off an old map, but just to see what we can see from the southern sky. So the galaxy cuts a pattern across the sky. We don't want the galaxy, right? We want quiet spots. So we're going to do our cosmology observations in 3 very dark fields where we're going to go very deep. I'll show you some preview data, which is just from, if the transition happens, there we go. So I'm just going to zoom in on a little section of EOR 0 that will fit on the screen. So we'll zoom in here. So that is about 2 minutes of data. There are about just sub 2,000 sources that we can pick out in 2 minutes worth of data. All this large scale pieces, these are clouds from our own galaxy's emission. High galactic clouds, again, of synchrotron emission that are out there. Again, this is what you see in the noise there. And this is about 30 degrees wide by about 15 degrees across in that image. I'll show you a few power spectra, mostly because we've been having fun with it. This is K perpendicular, K parallel. You see the very bright emission. This is what we call dirty, no sources subtracted. If you just put in the point sources, we haven't dealt with the cloudy emission yet, but if you just put in the point sources that we see and predict what it would look like in the instrument, you, of course, have power here, which is then thrown, given the detailed layout of the instrument. One other thing we do is we propagate all our error bars, so that's just showing that we understand our error bars in the power spectrum space. But if I then zoom in on the dirty, I subtract the image from the sky. I go from a dirty power spectrum to a residual power spectrum. You'll notice that the power in this region has dropped dramatically. That is point sources which have removed. But when I remove those, I also remove some of their power that was being thrown. And you do a better job, but it's dropping that, opening the EOR window. This here is the cloudy, large diffuse emission on the galaxy, which we haven't tried subtracting yet. That's next week. And if you go, just zoom in, I guess, a little bit here, the part in the top where it starts going there, that's all noise dominated. And below that black line, that's the first time anyone has seen noise-dominated performance within what's called the horizon line on any telescope. This is only 3 hours of data. We are processing much, much deeper, but that is what we do. A few other little things in there. You see those horizontal bands? up there. Yeah, that's actually interesting. It's kind of a, in retrospect, a design mistake in the telescope. Our Fourier transform, because when you bring in the electric field, you need to channelize it into frequencies. But taking our raw digitization rate is 660 megahertz, cycles a second, 0 to 330 megahertz. Breaking that into 10 kilohertz channels is a big FFT. And so we decided we'd do it in 2 steps. This is one of those things that sounds so clever. So you do it through a first polyphase filter, which breaks it up into 1.3 megahertz channels. It's a 256 polyphase filter. And then we select 31 of those. We've just decimated by a factor of 10 to get a 31 megahertz bandwidth, and then we do it again. Beautiful. We save so much money. The problem is the polyphase has a shape to it, like this, which gives us, and they're little, in our implementation, there are little aliasing gaps between them. That pattern, when you take the Fourier transform of it, gives you a series of lines. Damn. We had another one that showed up. There's a 4th line that showed up that a few of you might like this. Took us a little while to figure out. It turned out to be a cable reflection. So a number of the antennas have a 150-meter cable. The signal comes in. There's a slight reflection at the terminator. It goes back out to the antenna, reflects again off a slight impedance mismatch, and comes back. And so now you have the original copy of the signal and a very, very faint copy of the signal that's been time delayed. But at different frequencies, that will line up either in phase or out of phase. And so it will add constructively or destructively as a function of frequency, which gives you a true ripple in your antenna's sensitivity. If you don't calibrate that out, and normally we wouldn't care, right? We're not looking at part in 1,000 ripple. But our foregrounds, if you don't calibrate it, go up and down by a part in 1,000. And then when you take a Fourier transform of that, that shows up as a beautiful line in your power spectrum, because you've got something of that spectral structure. If you calibrate it, once you've identified it, you can calibrate it out, and it goes away. Anyway, you guys have been very, very patient. 2 other things that I won't talk about is Hera, which is the next instrument that we are proposing, and we're also doing a bunch of work here on those correlators, the MOF correlator, to enable larger arrays. Current correlators go as n squared because it's every antenna pair. These new correlators will go as n log n. It requires some stunts, and we have some support to do that. I also, unfortunately, did not have a chance to talk about the gaze array, which is on the top of Sieg Hall using John's lab, which is a little 8-element interferometer that we have here for undergraduate teaching. It's one of the few undergraduate teaching interferometers in the country. And so with that, I'd just like to conclude. The MW is working, and the data is beautiful. We understand this EOR window. We're collected a petabyte, and we're running on to petabyte number 2, collecting this data. We're continuing to build. And so thank you all for your attention.
We have time for a few questions. Are there any questions that you're holding on to there? I had one while you think of one. When you showed the movie of the reionization,
Yeah.
Were the fronts propagating out at the speed of light, or was there something? Was it optically thick?
It's optically thick. So the question is, when those bubbles form, how fast does that front go? And it's actually determined by how bright the galaxy is, because it turns out that the neutral hydrogen is very good at absorbing light. And so each photon is absorbed and it ionizes something, and so it actually is the photon rate. Now, it turns out to be pretty close to the speed of light, but it is subliminal.
Any other questions out here? Yes?
So how did you, earlier on in your presentation, you were talking about looking backward in time?
Yes.
Background,
It's a great question. Let me see if I can come up with the right analogy. I guess the way I would say it, it's really just a speed of light issue. So I can't look here in the past, but the people at the back of the room I'm actually seeing in the past because it took time for the light to get here. So I see them, it's not very long in the past because light is pretty quick. But the farther and farther I see back, I can't see me, but I can see somebody else as they were in the past. And thus I can make statistical inferences for probably what was happening here then. And so you just keep looking farther and farther and farther back. And it's fascinating that if you look about just shy of 13.7 billion years, it's a long time, but light keeps moving, you see a glowing wall. And thus, up until about 3 weeks ago, we didn't have any information beyond that because light can't travel through the plasma. And so that was the last thing the farthest thing we could see, that's the oldest thing we could see. Now, the interesting thing is you may have heard about BICEP 2 and the gravity wave potential detection in the polarization of the light of the cosmic microwave background. That polarization pattern was produced by gravity waves propagating through that early plasma. Now, while light can't travel through the plasma, a gravity wave can. And that gravity wave moved and then imprinted a pattern on the cosmic microwave background, which they are now seeing. So that's, in certain ways, our first probe of something which is beyond that wall that we see. Did that answer your question? It kind of got
So is it kind of like getting envelope?
Yeah. Yeah, and the reason people keep building bigger and bigger telescopes to look farther and farther back is that's the way we can look at earlier times. It's just by moving to something that's farther away, it will naturally be old. The light will have left it earlier, thus when it was older.
Miguel, you mentioned using GPUs at Murchison.
Yeah.
I think you all use some FPGAs as well. Could you
Yes.
say a little bit about what you and your students do with that?
So in the system, and there are various pieces. So the way the system is run, so the signal comes from the antenna. It's digitized, and then the first polyphase filter I was talking about is in an FPGA. And then the packetization is actually in an FPGA to put it onto the fiber. That then goes to the building, which is 10 kilometers. So how will we worry about RFI? Where the computers are 10 kilometers away, behind a hill, in a double 90 dB Faraday cages. That's how you have to seal those damn computers away. Anyway, you go into the computers. The first rack is an FPGA rack to do the fine channelization. And then it's shifted into GPUs to do the cross multiplication. And that is very pragmatic in terms of what is the cheapest now, and the technology keeps moving. And so we've both used these correlator boards developed by the Casper collaboration. And they're great for programming FPGAs and being able to do things. So your passive radar, the correlator stuff we're working on, we didn't actually develop that FPGA code. That was developed by the front-end filters were developed by the Indian collaboration, who's done some very nice work with that.
Well, thank you, Miguel. If some of you have any other questions and would like to come down after, that would be great. But Miguel, thanks so much for speaking to us today.
Thank you.